Thank you everyone for joining another tinyML talk. Today's talk is about high efficiency embedded computer vision, presented by Sandeep Mistry and Alex Chang. Next slide. Okay. Before we get started with the talk, we'd like to thank our tinyML strategic partners for committing to take tinyML to the next level together. We'd like to thank AZIP, Arduino, ARM, BrainChip, Edge Impulse, Embed UR, Efficient, Greenwaves Technologies, Gravity Inc., Himax, Imagimob, Infineon, Terra, Noda AI, NXP, P&G, Corvo, Qualcomm, Renesas, Schneider Electric, SensiML, Sony, Silicon Labs, ST, Synaptics, Sentient, and TDK. Thanks. You can also join our growing tinyML communities on Meetup and LinkedIn.com. Our Meetup group has over 20,000 members in 50 groups in 42 countries, and our LinkedIn community has 4,000 members and 16,000 followers. You can scan these QR codes to join these groups or go to the links pictured below. Also subscribe to the tinyML YouTube channel for updates and notifications and all the recordings of the tinyML web talks, including this video at youtube.com/tinyml. There's over 12,000 subscribers, almost 700 videos now with almost 500,000 views. So it's a really exciting space, and all of the videos will be recorded and uploaded there. Also join us in person at the next tinyML EMEA 2024, Amplifying Impact, Unleashing the Potential of tinyML, from June 24th to 26th in Milan, Italy. You can register now at the QR code listed here. We'd like to introduce today's speakers. Our first speaker will be Sandeep Mistry. Sandeep is Principal Software Engineer at ARM and is based in Ottawa, Canada. He has a passion for enabling developers through his open source contributions by making complex technology simpler. We'd also like to welcome Alex Chang. Alex Chang is a Senior Product Manager for IoT at Himax Technology, a leader in display drivers and AI chipset solutions for edge devices. He has over 20 years of experience in sensors and IoT technology and currently oversees product strategy for AIoT solutions across various verticals. Alex leverages his technical knowledge to drive innovation in endpoint AI chips and modules, empowering Himax customers in the United States to enable AI everywhere. So, we'd like to introduce today's talk. Thank you, Alex and Sandeep, for joining us.
Hey, good morning, everyone. This is Alex. So today I'm gonna introduce a little bit our AI solution together with our algorithm. So I'm gonna cover the company profile technology, also the whole hardware architecture together with a block diagram and development tool and third-party benchmark report. And Cindy is gonna be cover all the ML and demos. Okay, so let's get started. So Himax actually is a fabulous semiconductor company, which have over 20 years. It comes to the driver electronic and went to the LCOS and the other micro display. So they are we be founding since 2001 and as a Nasdaq listed company. So they are 26 office in worldwide. There are 3 office in R&D center in California, 2 of them, and the one in Minneapolis. So we also have another 23 office in worldwide. So there are 9 R&D center in the worldwide, and our headquarters is in Taiwan. So we have around like 2,100 employees. The funny thing that's 90% of our employees are R&D based. So just give you a quick view of Himax. So what we're doing, Himax actually, we develop in human interface and display technology related to IC development, including display driver, TDDI, timing control. Actually, we are growing the trend of LCD panel from the large LCD size and covering the TV, monitor, and the notebook in 2000s. To small, and medium-sized display covering the smartphone, tablet, automotive in 2010s. So other than the display and driver IC business, we also invest a lot of the resource for non-driver business from since the mid of the 2010s. So covering the optical related technology like AR cars. So actually, this is the Google Glass first gen of the Google Glass that we made by Himax. So we also cover in the AR micro display for AR glasses and holograph HUD wafer level optic applied to the DOE lenses, MLA optical compartment in the leading AR, VR, LiDAR, SL, time-of-flight devices. We also work a lot of cool technology like 3D sensing, like a 3D structural line, and the time-of-flight on smartphone, and the last one that we invest a lot of resource in the CMOS sensor and the AI processor. That's what we're gonna cover in today. So like I mentioned, Himax also not just doing the AI processor, display driver, 3D sensing. We also have a cool technology doing the CMOS sensor. While listed here is always on sensor product family. So every single sensor here, we have a dual mode running with a low power mode for always on application like the battery operated devices. We also have full speed mode. For example, from the QVGA all the way to 5 mega sensor, especially to introduce this one that's a 1-to-1 aspect ratio sensor we can use for the doorbell. So you can have the 180 fish eye lens to cover head to toss from the face detection all the way to package detection. So with the power saving mode with a 3 frame rate per second, as we can lower as 300 microwatt with a full speed 3.6 milliwatt. So every single, that's our always on sensor family dedicated for the battery driven devices. So the AI processor. So when we talk about the AI, most of the people or machine learning computing, most people will think about the cloud data center or need a huge input data and the power hungry computing server to train the model and the complete image recognition. Or understand the human language, the power consumption is over 100 watt over here. So the also the cloud server and it's not possible to run this kind of task in local devices. Along with the silicon technology, the AI algorithm improves. So many people move their technology and I train machine learning model into like hundreds milliwatt, like we call edge AI. So cloud AI and edge, that was before edge AI is happening. What we're doing right here, so in AI OT area, everything has to be moving extremely edge because you don't want the data security, the inference time. So Himax is one of the pioneer to really bring the AI, like complex AI model into like a 2 digital milliwatt. Everything we run is kind of like a lower than 100 watt, even like a 10 watt, 10 milliwatt, sorry, 100 milliwatt or lower than 10 milliwatt. So we have the white side first gen and white side second gen. So by use those application, we are in the endpoint AI. We actually can run the motion detection, people sensing, people counting, face detection, facial matching, and face recognition. Oftentimes, like a facial matching, that people running with more than 4 watt, 6 watt in the edge AI, but we actually can be running with 2 digital of milliwatt. That's what we focus. So Himax with specialty that we will bring the complex AI running ultra low power. So ultra low power in the AI processor, that'll be Himax specialty. But how we can run this low power, we actually, our value population, we have three cores. We have a small MCU running with M55 100 megahertz. We have large MCU running with M55 400 megahertz. We have a dedicated NPU with a U55. In this case, those three core optimized tech architecture with 5 different hardware we got state machine from the deep power down, small core, large core, and NPU. We can balance out the performance and the power consumption. For example, with some of the notebook application software flow, we only run with like a small MCU, like 100 megahertz to save a lot of power. Some of the AI we run with our sensor for the CND or the motion detection without even wake up our MCU. So some of the application very complicated, so we need to load different AI model like a facial mesh. We have to load like at least 4 different AI model, face detection, facial landmark all together. We have to run with dedicated NPU. By doing that, we also have a very think for the power management schema with the DVFS and the DC to DC. This kind of algorithm help us save a lot of power. So when we talk about the power saving running with a complicated AI model, we're not talking about only the AI process only, but also because we talk about whole system from the image input all the way to computing in the our AI processor. But because Himax has a dedicated always on low power sensor, bonding with our AI processor, so we can do the whole system, lower down the whole system power extremely well. So we also provide the software tool chain because we use the ARM-based architecture, so there are a lot of the community tool chain support online by providing the no-code or low-code AI platform support. So with those customer, they really want to load down the power or they want to do the production. We release the SDK and low-level driver algorithm. We have our own AI team. We can build whatever like customer need. We work with third party with their algorithm to really bring the product to production level. Not many of the AI company can really bring the product to production level. Himax is one of them. So for the from here, you can see that this small device here, actually that's our Wi-Fi module. Why we bring the Wi-Fi module? Because for last mile of the IoT company, they couldn't really have who doesn't have a ability to build a system integration. We provide a whole module which include the lens, sensor, AI processor, flash, algorithm, AI algorithm all together. What they need to just slide in, that's the ZIP 24-pin standard one. So by enable the HPD face detection, face recognition, so the sensor has been enabled, the focus have the optical has been optimized. So all together as a tool chain here to make a maker or the company who want to go production easier. On the right-hand side, we actually have like our ecosystem from the software tool chain. We work with the TensorFlow. We have a SaaS. We have a reference design together with Microsoft Azure and Edge Impulse C Studio. With the community, you can check a tinyML, C Studio, Edge Impulse, Platform, and the DigiKey. Those algorithms we work with Armoron, Cyberon, AIZ, those kind of big company and the manufacturer of as well. If you guys have some product want to really go to production in the future, so we have a partnership with those manufacturers like the Chang, Bison, SWNC, this and that. This is our white-side solution. So we have a SDK. You see the blue rectangular thing here. That's our AVB. The red that rectangular highlighted, we have a lens. You see right here, the CI sensor with lens. In the middle of the QR code, that's our white-side AI processor. So that you can see next slides to so you can tell that's a quarter coin. So how small and sexy of our module. This not just this come with a lens for FOV 87 by 69 and a power supply with 3.3, 2.8, 1.8. We also have the standard algorithm, human body detection, face detection, head pose, face recognition, all together inside of this module. With the EVB, you have IIoT, USB microphone, speaker, and a lot of the interface like I2C, SPI, Core SPI, and GPIO PDM. Next, gonna go over our block diagram. So like I say, we have a 3 core, we have a 400, 100 running with M55, and another dedicated NPU U55 running with a 400 megahertz. We also have huge SRAM, 2 mega SRAM. This can enable we load very complex AI model. Sometimes we run 8 different models at the same time, still maintain a 15 frame per second pretty smoothly. Also with those access control or security application, we can do the buffer video for 10 seconds. 5 seconds, depends on the frame rate. So before the event happen, somebody need to break your house, we can record 10 seconds before they approach. So that's the good thing of the SRAM. We also have as I mentioned earlier, we put up to the energy efficiency, like a DC-DC converter, DVFS. By running the local AI. So the security is one of the key issues. So we have many different algorithms, mechanism to secure our data. So we have a PUF that's kind of like a fingerprint mechanism inside the chip. So without the decoder, you couldn't really reverse engineering to take the data out. So we also have a Quibito accelerator by running with AES 255, SHA 256, and everything bonding, we can use the ARM trust zone to secure data. Below that's our peripheral. I just want to mention another thing. We have 3 different hardware accelerator. So this is white-side processor. We have a motion detection hardware accelerator. So we have a JPEG decoder and the VAD to really detect the voice detection. So we can run computer vision, we can run the computer voice detection all together. So that's a very good solution for the audio and video AI process. Here is our development system. So the system requirement, the software you will be needed like Visual Studio Code, debug, highlighter, and together with the Pi OCD for interrupt or the break, and you have a GNU GCC, a GNU compiler collection. Altogether, hardware the ARM's architecture, we support the CM, SIS, DAP, So this is the architecture here is that everything, most of them are free to download on our GitHub. So check out the GitHub, Himax GitHub. So we have a very clear instruction together with SDK all together of those tools. So you can easy to download for free. Some of them might request a license, not too much. So altogether, we have like a very solid ecosystem, easy to use, implementation, deploy altogether by using maybe the MCU link or the CNSIS diff, the debugger port to deploy the code into the ARM chip. This is our WiSci processor, AI processor, to collaborate with one of our ecosystems, C Studio. You see the red rectangle right here, the small little rectangular stuff. That's our WLCSP 65 pin AI processor. So together with a C Studio board, you can enable the microphone connector of CSI, micros SD card slide with a shell line connector right here, two lines extension, so you can actually enable the connectivity like the Wi-Fi 6 module, or you can enable the LCD module to stack up all the way. So this is expandable devices. That's pretty cool. I have another slide showing how good the performance it is. Like I say, that's a comparison, benchmarking comparison by I just download from internet. That's one of third party. We don't know that they grabbed all the 2024 MCU AI vision both out of shop. They kind of use like so they use the same model 96 by 96 image input together with a shift YOLO algorithm by doing the human face picture on the same condition. So you can see they use a Himax WiSci1, Himax WiSci2, ESP32, ESP32, and STN H7 and the Broadcom BCN 2711 altogether, and that they are three different category power consumption. The lower the better. Inference time, the lower better. Same thing. Frame rate per second. You want the highest number as you can. So in the power consumption, our first gen kind of running with 0.4 watt. Second gen 0.35 watt. ESP32 around like 0.45. The STM running with H7 running with a 0.59 watt. Like I say, one of the Broadcom running with a 3.79 watt. So that's around like close to 4 watt. That's what I'm saying with a 96 by 96 resolution with only face detection. Most people running more than 3 watt, but we can run this kind of the application like you can see right here. That's only like 0.35 watt. Actually, that this haven't been implement our low-level driver and optimize the state-by-state wake up hardware state machine like I showed earlier. By enable those features, the power can be down to 0.05 watt, which is a 50 milliwatt in this case. So we can run the facial match like 88 milliwatt, very, very low. So inference time, same thing. Like I say, the lower the better. Our WiSci1 first gen will be running like 389 millisecond. Second gen 33, so 10 times different. ESP32 180 milliwatt millisecond. Sorry. The STN 178 millisecond. Of course, the Broadcom can be running with only 8.83 millisecond because it's such powerful, but they drain the power a lot too. Like I mentioned, 3.8 milliwatt, 3.8 watt. So frame rate per second. So our first gen we can only run close to 3 FPS. our second gen, we can run 30 FPS, ESP32 5 FPS, STH7 5, the Bocon 130. Actually, like I say, this haven't been enabled those balance the best performance by enable the low level driver. By doing that, we can run up to like 60 FPS. So for all the details, you can scan the QR code right here to check the detailed report. Actually, that's step by step build out the whole system where you can purchase and how you actually download the development tool and evaluate all the performance very detailed. You can check out. So in this chart, we are in the best of the category. So that's just overview and see how good of a performance that by using the WiseEye 2 Himax solution. Okay.
So now I'll go over a few models and show you how you can port them to run on the Himax WiseEye 2 processor. So the first one is going to be pose estimation. So you can use this as a feature extraction layer for fall and movement detection or human-machine interfaces. So the idea is you have an input image with one or more people in it, and the model will predict a bounding box around each person in the frame, as well as several key points on their body. So for this model, we use a pre-trained version of the Ultralytics YOLO V8 pose model, and we weren't using the original GitHub repository, but we use a fork from D. Gurim, the GitHub user there. So the reason we use this fork to export the model was it removes some transpose operations and separates the model's 7 outputs for improved accuracy with quantization. And this model would output a bounding box for each person in the input image, and each of their 17 key points in the person's pose. So to export this model, you would start off by cloning the GitHub repository, as indicated on this line here. And then you will use pip install to install the Python dependencies which are needed to use this model. And then you can run the following Python code here to export the model. So you'd import the Python package and then create a new YOLO object with the name of the model here for the pose detection. And this is going to download the model and set things up. And then you can call model.export to export the model in TensorFlow-like format. And for this application, we're going to use an input size of 256 by 256. Use the Cocoa dataset for quantization. We want integer 8 version of the model, and we want to separate the outputs and export for hardware optimization. So once this is complete, you'll have a TensorFlow-like file to use. Then you can open this model in an application like Netron, which I've included here. It's quite a large model with many different layers, so not all of them fit on the screen. But the key parts are, you can see there's a 256 by 256 by 3 input tensor, and then there's a 7 outputs, which I'll go into more details shortly. Okay, so that's not enough to run on the ARM Ethos U55 NPU. There's one more step needed, which is to use the Ethos U Vela compiler, which can be installed using this pip install command here. And then you can run it with a few parameters, including the path of your TensorFlow-Lite model. So as Alex mentioned earlier, the Ethos U55 on the Himax WiseEye 2 has a configuration of 64 multiply accumulates per clock cycle. So you need to specify that there. And then you also need to download the Himax Vela config file, specify the path to that, and some other parameters. And then once that's run, Vela will compile the model, and then anything that can be run on the NPU is collapsed into a block like this. So this is basically the same model in this slide, but converted to run on the ARM Ethos U55 MTU, and you have the 7 same outputs. So the ML inferencing is only one part of what you need to do in your application. you're going to need to use the WiseEye2's camera interface to capture an RGB input image. So for this application, we're using a resolution of 320 by 240. And since the ML model needs an input of 256 by 256 by 3, we need to crop and pad the original input image to that size, and then subtract the quantization 0 point for the TensorFlow Lite model. And once that's ready, we can feed that as an input to the TensorFlow Lite, and it's going to output us 3 sets of bounding boxes because the model has a grid box layout. And then for each bounding box, you'll get an associated score and the 17 key points. And you can't directly use this output in your application. You need a post-processing step. So this will do things like dequantize the output from int8 to floating point 32. We can apply some sigmoid and softmax activation functions, apply the grid box scale and offset, and then use an algorithm called non-maximum suppression. Because many times the output of these bounding boxes are going to be overlapped. So we want to use a score and a threshold to remove the overlapping bounding boxes. So we just have one prediction per person in the image. So once that's done, you'll get n bounding boxes, scores, and key points, and being the number of people predicted in that input image, and you can overlay the outputs. So I've run this model on the Seed Studio board with the Himax WiseEye2 processor on both, just using the ARM Cortex-M55 CPU without helium vector instructions, and then again using the EthosU55 MPU from ARM. Both types will need 728 million multiply accumulate operators, which is quite large, and you'll need 853 kilobytes of RAM if you're using the M55 alone, and 3.2 megabytes of flash. And this will take about 61 milliseconds or 61 seconds to run on the board. Contrasted to using the EthosU55 MPU, it'll run in 93 milliseconds, which is 611 times faster. Okay, so I'm going to show a demo now of my colleague Stephen in the background, and there's the Seed Studio board here with a camera attached in the back. And I've connected a LCD screen, which will show you a live view of what the camera is seeing with overlays of the output of the model. And this board is also powered by a battery. You can't fully see it. It's under the screen, but you can see the cable there. So I'll play this back, and you can see the model working in real time on the tiny WiseEye2 here. And this is getting just over 10 frames a second. So it's quite a good performance for a microcontroller. Okay, great. Okay, now I'll move on to the next model, which is a face mesh model. So this can be used as a feature extraction layer for detecting familiar faces or attention monitoring, emotion models, or medical diagnosis. So the idea is you have an input image, and then we detect all the faces in it. And then for each face, you can get several key points in there of that face here, as indicated by the pink dots here. So how we ported these models to the board was we used 2 pre-trained models from Google's MediaPipe project, which were originally in 16-bit floating point TensorFlow Lite format. Then we quantized them to integer 8-bit format using a tool called TF-Lite to TensorFlow. So the first model is called MediaPipe BlazeFace. It's a lightweight object detection model for detecting one or more faces in a 128 by 128 RGB input image. And this model has a SSD-like convolutional neural network architecture with a custom encoder. So this model is going to give us the faces, and then for each face, we can run the MediaPipe face mesh model to predict 468 facial key points in a 192 by 192 RGB input of the crop face. This model has a MobileNet V2 like CNN architecture with customized blocks. So to convert both models, you would set up the TF-Lite to TensorFlow tool on your computer or on Google Colab. Then you can specify the path of the floating point 16 TF-Lite file, and then specify you want a full integer quantized TF-Lite as the output. And this will give you a integer 8-bit version of that original TF-Lite model, which was floating point 16. And after that step, as I described earlier, you need to use ARM's Vela compiler to convert that integer quantized int8 model to run on the ARM ethos-u 55 MPU with this command. So in this slide, on the left-hand side is a screenshot of the original floating point 16 model. And then on the right-hand side is the same model converted to int8 and compiled with Vela. So in this case, not all the operations could be run on the ethos-u 55 MPU. So the pad operations will have to run on the M55 CPU. But the whole graph can be used with TensorFlow Lite on the Seed Studio board. Okay, and to use this image, to use this model, we need to capture an image from the camera. Again, we're going to use a resolution of 320 by 240, and we're going to pre-process it with a bilinear resize to match the 128 by 128, which is needed by the model. Then we can use TensorFlow Lite to perform the ML inference, and we'll get several bounding boxes and scores for each face detected in that input image, and we'll post-process those by doing a quantization, sigmoid activation, applying the grid box offsets and scales, and then non-maximum suppression. Then we'll get n bounding boxes, n being each face that's predicted in the input image, and a score for it as well. So for this input image, we can see the red box around the face was detected as a face by the model. Okay, so some more stats for this. So this model is going to require 31 million multiply accumulate operations. So it's not as large as a pose detection model I showed earlier. And if you're running just on the Cortex M55 CPU, you're going to need 461 kilobytes of RAM and 203 kilobytes of flash. It'll take about 3.4 seconds to run each inference. And contrasted to if you were using the ethos-u 55, you need slightly less RAM and flash, and it takes 31 milliseconds to do an inference, which is 109 times faster than just using the M55 CPU without helium. And again, so this is the model graph of the face mesh model, and then I used the steps described earlier to convert it to run on the MPU. Again, there's some operations that can be run on the ethos-u MPU and these blocks here. And then the 3 pad operators need to fall back to running on the M55 CPU. And the pipeline to process this model is you take the 320 by 240 input image you had, and you crop and pad it where the face was detected. And then you do a bilinear resize to 192 by 192 and subtract the quantization 0 point. Then you can use TensorFlow Lite for microcontrollers to do the ML inference. You'll get an output of a score and the 468 key points. And then as a post-processing step, you can dequantize the intake output to floating point and run a softmax, a sigmoid activation function on that. And then you get the score and the key points for that face, which you can see here in the output with the outputs overlaid. This model is slightly larger and requires 36.8 million multiply accumulate operations. And it will take 482 kilobytes of RAM and 748 kilobytes of flash. If you're just using the M55 CPU, it'll take about 4.4 seconds to do an inference. And if you use the ethos-u MPU, it'll need slightly less RAM and slightly less flash, but it'll be 103 times faster and take 43 milliseconds to do an inference. So I'm going to run a demo again. Steven's in the background, and you'll see him moving around, and it tracked the key points in the space. And this runs just under 11 frames a second on the Seed Studio board here. Okay. Okay, and now I'll wrap things up with the conclusion. So the Himax YSI2 HX6538 processor is the perfect way to get started on your next power-constrained embedded computer vision project or application. The SoC's rich peripherals and memories, combined with ARM's Cortex-M55 CPU and Ethos U55 MPU, enable privacy-preserving on-device real-time processing of a live camera input or other sensor inputs on IoT endpoints. We demonstrated how pose detection and facial mesh models, which were previously targeted for mobile hardware, can be deployed efficiently on endpoint devices, and how quantized models that require tens to hundreds of billions of multiply accumulate operations for inference can be run on the Ethos U MPU. And if you want to learn more, there's a few links here for you to follow, including details on the Cortex M55, Ethos U55, Himax YSI2 processor and SDK, the link to buy the board from Seed Studio, DigiKey, and some use cases. Okay, that's all I had today.
Great. So thank you everyone for joining the talk today. And if you have any questions that you didn't get answered, again, go onto the forum for this talk at tinyml.org/forums. But we'd like to thank our executive strategic partners, Qualcomm, a platform to scale AI across the industry. Next. Sentient, making edge AI a reality. Next. We'd also like to thank our Platinum strategic partners, Embed UR, software services to edge ahead. Next. Atrios, deploy vision AI at the edge at scale. From Sony. Next. I also like to thank our gold strategic partners. Next slide. ARM, build the future of tinyML on ARM. Edge Impulse, the leading development platform for EdgeML. Infineon, driving decarbonization and digitalization together. Renesas, they're enabling the next generation of AI-powered solutions that will revolutionize every industry sector. ST, providing extensive solutions to make tiny machine learning easy. And we'd also like to thank our silver strategic partners, AZIP, Arduino, BrainChip, Efficient, GreenWave Technologies, Gravity Inc., Himax, Imagimob, Initera, Noda AI, NXP, P&G, Corvo, Schneider Electric, SensiML, Silicon Labs, Synaptics, and TDK.